If you asked a state-of-the-art supercomputer to find, like, the single most efficient delivery route for a fleet of just 50 Amazon trucks, checking every possible option wouldn't take a few seconds.
No, it would literally take longer than the universe has existed.
Which is just wild to think about.
Hmm.
Today, we are looking at the math that attempts to solve those impossible problems. Because, well, you asked us to be a god, teach you everything, make you remember it all, and help you completely ace your exam? Well, challenge accepted.
I mean, that is quite the ambitious mission you've given us, but if you are staring down the barrel of your CST 306 algorithm analysis and design exam at APJO Abdul Kalam Technological University, you are in exactly the right place.
Yeah, and we aren't just going to sit here and read you a list of textbook definitions.
Right, that doesn't help anyone.
Exactly, especially when the clock is ticking and you're staring at a blank piece of paper in an exam hall. Instead, we're going to build a mental map together. Okay, let's unpack this. We're looking at a journey of 5 distinct concepts.
Sort of, building from the ground up.
Right. First, we figure out the measuring stick, how we even judge if code is good or bad. Then, we look at organizing the chaos of data. Once the data is set, we open the general's playbook to master the core problem-solving strategies.
And then we hit the wall of those impossible problems you mentioned.
Yeah. And finally, we'll break down the exact mathematical metagame of how your exam is actually graded so you know exactly where to put your energy.
It really is a beautifully structured course. Like, it takes you from the micro, counting individual operations, all the way to the macro, asking fundamental questions about the absolute limits of human computation.
Which is pretty heavy stuff.
It is. And the key to remembering all of this for the paper is understanding why these concepts were invented in the first place.
So let's start with the measuring stick. Module 1. Before you can write a blazing fast algorithm, you have to know how to measure a slow one. And we aren't talking about measuring in seconds, right?
No, absolutely not.
Because, like, a terribly slow algorithm running on a modern supercomputer will still technically finish faster than a highly optimized algorithm running on, say, an old flip phone.
That's the fundamental problem right there. We can't use seconds. That's why computer science uses asymptotic notations. We need a purely mathematical way to describe how the execution time or the memory space required grows as the input data gets massive.
Right. So we look at the best, worst, and average case complexities.
Exactly. To do that, the course introduces this whole alphabet soup of notations. You've got big O, big omega, big theta, little o, and little omega.
Which sounds overwhelming, but I always try to map this to buying a car. Isn't big O basically just the worst case scenario miles per gallon for your code?
Oh, that's a good way to look at it.
Like, it tells you the absolute worst performance you can expect. You know, this car will never get worse than 10 miles to the gallon. It bounds the growth from above.
Yes, that analogy holds up perfectly. Big O gives you the upper bound, then big omega gives you the lower bound. So the absolute best case scenario.
Okay, makes sense.
And big theta is when your upper and lower bounds grow at the exact same rate. It's a tight fit. Little o and little omega are just stricter versions of those bounds.
Stricter how?
Well, the growth rate is strictly less than, or strictly greater than, rather than just less than or equal to.
Got it. And looking at the sample exam, they really love testing if you actually understand how these scale in the real world.
Oh, definitely. What's fascinating here is the exam explicitly asks you to arrange a specific list of functions by their asymptotic growth rate.
So you really need to know this stuff cold.
You do. You need to know instinctively that a constant time algorithm order of 1 is faster than logarithmic time, which is log n. Log n is faster than linear time, n. Linear beats quadratic, n squared.
And exponential time.
Exponential time, like 2 to the power of n, will absolutely crush your processor as data grows.
Right, like our Amazon trucks. But calculating those bounds gets significantly trickier when code calls itself, right? Recursive algorithms.
Oh, for sure. When a function calls itself, you can't just, count the loops. You have to solve recurrence equations.
And the syllabus mentions a few ways to measure this, right? The iteration method, recursion tree method, substitution method, and the master's theorem.
Yeah. The recursion tree method visually breaks down the cost at each level of the call stack. But the ultimate shortcut, and this is a guaranteed point score on your paper, is the master's theorem.
And crucially, the syllabus explicitly notes proof not required for the master's theorem, which is very merciful.
It's essentially a formula cheat code. You look at a recursive equation in the form of T of n equals a times T of n over b plus f of n.
Sounds like a lot of math.
It's just weighing two things, really. How fast the problem is branching into sub-problems versus how much actual work is being done outside the recursion to stitch it all back together.
Okay, so branching versus stitching.
Exactly. The theorem compares those two weights and just hands you the big O complexity instantly. And the model paper specifically asks you to solve an equation like T of n equals 8 times T of n over 2 plus 100n squared using it.
So knowing that theorem is completely non-negotiable.
Absolutely non-negotiable.
Okay, so we got our measuring stick.
Yeah.
But fast code needs a place to live, which brings us to the second stage of our map, organizing the chaos.
Module 2.
Right, because how data is structured directly dictates how fast an algorithm can run. The syllabus focuses heavily on advanced data structures, specifically AVL trees. But let me push back on this for a second.
Sure, go ahead.
Why do we even need an AVL tree to self-balance? Isn't a standard binary search tree good enough? You put smaller numbers on the left, bigger numbers on the right, and your search time is magically cut in half every single step.
Well, in a perfect world where data arrives completely randomized, yeah, a standard binary search tree works great. But think about what happens if you insert already sorted data into it.
Like putting in the numbers 1, 2, 3, 4 in order.
Exactly. Say you input 1, then 2, then 3, then 4. Every new node is bigger than the last, so it always goes to the right.
Oh, I see. It doesn't branch out at all. It just becomes a single long diagonal line.
Right. It basically degrades into a simple linked list. Your beautiful, fast login search time completely collapses into a terrible linear end time. You'd have to check every single node one by one.
That's horrible.
It is. AVL trees solve this by strictly enforcing a balance factor. If the height of the left and right subtrees differs by more than one level, the tree physically rotates its nodes to maintain balance.
Visualizing those rotations like left, left, right, right, left, right, and right, left seems like something you can't just memorize from a textbook. You have to physically trace that on paper, right?
You absolutely do. The model paper actually gives you a diagram of an AVL tree and asks you to perform specific operations, like inserting the number 70 and deleting the number 55.
And then you have to redraw the newly balanced tree.
Yet, redraw the whole thing.
Wow. Okay, the syllabus also throws disjoint sets into this section. What exactly are those doing?
A disjoint set is a data structure that keeps track of a set of elements partitioned into a number of disjoint, meaning non-overlapping subsets.
Give me a real-world example.
Think of it like tracking friend groups at a massive party. You need to quickly know if two people are in the same friend group. That's the find operation, which usually points to a leader of the group.
Okay, and if groups merge?
Right. If two different groups mingle and become one big group, you need a way to efficiently merge them. That's the union operation.
Got it. And to navigate all these interconnected nodes and groups, you need graph traversal algorithms. The course expects you to know breadth-first search, BFS, and depth-first search, DFS.
Two absolute classics.
Which I always picture as exploring a maze. Like BFS explores like a ripple in a pond, checking every single immediate intersection before moving outward. DFS is the person who runs as fast and deep down one single hallway as they can until they hit a dead end.
And only then do they turn around and backtrack. That visual works perfectly. And the course pairs those traversals with topological sorting.
I'm assuming that's not just regular sorting from smallest to largest.
No. Topological sorting is for directed acyclic graphs. Those are networks where connections have a specific direction and there are no loops.
Oh, so it's like a flowchart of college prerequisites.
Yeah.
You can't take algorithm analysis until you've passed data structures, and you can't take that until you've taken intro to programming.
That is the exact mechanism.
So topological sort basically gives you the linear order you have to take the classes in so you never violate a prerequisite.
Yes. It creates a linear ordering of vertices. And alongside that, you also need to find strongly connected components.
What's that?
It's a concept where, within a massive directed graph, you find the specific clusters or subgraphs where every single node can reach every other node.
Like a cluster of one-way streets in a downtown grid where you can circle around to any storefront, even if the rest of the city is cut off.
Right. It reveals the tightly knit communities within a sprawling network.
So now our data is organized, balanced, and we know how to navigate it. We are ready for the battle plans.
Modules 3 and 4.
The third stage of our map, the General's Playbook. This is the meat of the entire discipline, really. We are talking about the distinct philosophical approaches to solving massive computational problems. Divide and conquer, greedy strategy, dynamic programming, and backtracking.
Let's look at divide and conquer first. The classic example here is merge sort. You have an unsorted array, you keep slicing it in half until you have single elements which are inherently sorted, and then you merge them back together in order.
The syllabus also highlights Strasson's algorithm for matrix multiplication here. What makes Strassen so special? Because multiplying matrices seems pretty straightforward, rows by columns.
It is, but standard matrix multiplication is surprisingly slow. To multiply two 2x2 matrices normally, it takes 8 separate multiplication operations.
Which doesn't sound like a lot.
Not for a 2x2, no. But when matrices get to be thousands of rows wide, those multiplications create a massive bottleneck. Strawson figured out a brilliant mathematical trick using divide and conquer. He found a way to multiply two 2x2 matrices using only 7 multiplication operations, substituting the missing one with extra addition and subtraction steps.
Because the computer can add and subtract way faster than it can multiply.
Exactly.
So saving one multiplication might not sound like a lot, but scaled out to massive data sets, it changes the entire big O complexity.
It really does. Now, moving to the greedy strategy. This is the approach where you make the locally optimal choice at each step, hoping it leads to a global optimum.
Taking the biggest slice of pizza right in front of you.
Something like that. The course focuses on the fractional knapsack problem, where you fill a bag with items to maximize value and are allowed to take fractions of items. It also covers Kruskal's algorithm for finding a minimum cost-spanning tree.
How does that one work?
You just keep picking the cheapest connection between nodes that doesn't create a loop until everything is connected.
Okay, but the syllabus also includes Dijkstra's algorithm for the single-source shortest path, finding the fastest route from one point to everywhere else.
But wait, I'm stuck on Dijkstra's.
What's the holdup?
If it's a greedy algorithm, doesn't that mean it could accidentally take a path that looks fast initially but actually ends up dumping you into a massive traffic jam later? How does a short-sighted greedy choice guarantee the overall shortest path?
That's a very common point of confusion.
What?
Dijkstra's is greedy, but it's not blind. At every step, it doesn't just pick the shortest next hop in isolation.
Okay, then what is it doing?
It picks the unvisited node with the shortest known total distance from the starting point. Because it updates those cumulative distances at every step, once it finalizes the path to a node, it has mathematically proven there is no shorter way to get there.
Ah, okay. The cumulative tracking saves it. But what happens when the greedy strategy's short-sightedness completely fails?
Then you turn to dynamic programming, DP. Right. I used to think of dynamic programming like meticulous meal prepping for the week. But that analogy never quite fit the actual mechanics for me. Let me try a different one.
Let's hear it.
Isn't DP more like doing a massive math worksheet? Say question 5 requires you to calculate 25 times 25. Then way down at question 40, you need 25 times 25 again. A regular algorithm would just do the math from scratch a second time.
Right, which wastes time.
But dynamic programming is like writing the answer on a sticky note the first time you do it. When you hit question 40, you don't do the math, you just look at the sticky note.
That is a much better way to grasp it. We call those sticky notes memoization, or building a table. DP solves complex problems by breaking them down into subproblems, but crucially, those subproblems overlap. It calculates them once, stores the answer, and reuses it.
And the syllabus explicitly highlights the principle of optimality here.
If we connect this to the bigger picture, the principle of optimality is a direct question on the sample paper. It states that an optimal solution to a problem always contains optimal solutions to all of its subinstances.
So like if the fastest drive from New York to Miami goes through Atlanta, then the segment from New York to Atlanta must also be the absolute fastest route between those two cities.
Exactly. If it wasn't, the overall trip wouldn't be optimal. You apply this in the course to things like the Floyd-Warshall algorithm, which finds the shortest paths between all pairs of nodes in a graph simultaneously using a stored matrix of distances.
Makes sense. And finally, when you can't be clever with DP, you just have to search through all the possibilities, but smartly. Backtracking and branch and bound.
Right. Backtracking is used for the n queens problem, placing n chess queens on an n by n board so none can attack each other. You place one, move forward, and if you hit a dead end, you step back and change the previous move.
And branch and bound.
Branch and bound takes that a step further for optimization problems, like the traveling salesman problem. It keeps track of the best solution found so far that's the bound. If you are exploring a partial path and its cost already exceeds your current best bound, you prune that entire branch of possibilities. You don't even bother searching the rest of it.
It's an incredible time saver. Now, for you listening, here's the ultimate warning for this section. You must know the control abstractions for these strategies.
Absolutely crucial.
A control abstraction is basically the high-level, overarching blueprint or pseudocode template for the strategy. The sample paper directly asks you to write the control abstraction for the greedy strategy and to explicitly compare the divide and conquer and dynamic programming methodologies.
Don't just know the specific algorithms, you have to understand the architectural blueprints behind them.
And understanding those blueprints prepares you for the fourth stage of our map, the boss fight. Module 5, Introduction to Complexity Theory. What happens when no algorithm, no matter how clever the blueprint, can save you?
We enter the realm of computationally intractable problems. This is where we classify problems not by how fast we can solve them, but by whether they are realistically solvable at all in our universe.
Right, we divide the world into tractable problems we can solve in a reasonable polynomial time and intractable.
Yes, intractable problems take so long the sun would burn out before your laptop finished computing them. This introduces the famous complexity classes, P, NP, NP hard, and NP complete.
Okay, let's break those down.
Class P represents everything we've talked about so far. Problems solvable in polynomial time, fast. Class NP stands for non-deterministic polynomial time. These are problems where if someone hands you a potential answer, you can verify if it's correct very quickly.
But actually finding the answer from scratch.
We don't know any fast way to do it.
So P versus NP is basically like Sudoku. Finding the answer for a blank 100 by 100 Sudoku grid from scratch is a complete nightmare. That's NP.
Exactly.
But if someone hands me a fully filled out grid, checking to see if there are any duplicate numbers in the rows or columns takes almost no time at all. Verifying the answer is easy. Finding it is brutally hard.
That is an excellent way to ground the concept. Now, within that space, we have NP hard problems, which are basically the most vicious problems in computer science. They are at least as hard as the hardest problems in NP.
And NP complete.
NP complete problems, like the clique problem or vertex cover, which the syllabus focuses on, sit right in the sweet spot. They are both in NP, meaning their answers can be verified quickly, and they are NP hard.
So if a problem is NP complete and basically impossible to solve perfectly as the data gets massive, what do programmers actually do? Do they just throw their hands up and accept defeat?
No, they compromise. That's why the second half of this module is dedicated to approximation algorithms and randomized algorithms. If we can't get the perfect answer, we settle for close enough or lucky enough.
How does close enough work mathematically?
Approximation algorithms guarantee a solution that is close to the optimal one within a specific mathematical ratio. The syllabus covers the bin packing problem, trying to fit differently sized items into the fewest number of standard containers.
How do they test that?
The model paper asks you to explain the first fit decreasing strategy. You sort your items from biggest to smallest, and then you just shove the next item into the absolute first bin that has room for it.
It won't give you the mathematical minimum number of bins, though.
No, but it is extremely fast and gets you a very good predictable result.
And what about lucky enough? Randomized algorithms sound wild to me. We are actually introducing randomness, like rolling a dice, into the code's logic.
We are, and the exam heavily tests the difference between the two main types of randomized algorithms, Las Vegas and Monte Carlo algorithms.
Let's start with Las Vegas.
A Las Vegas algorithm always produces the exact 100% correct answer. However, the time it takes to compute that answer relies on random chance. It might be lightning fast, it might take a while, but it is always right.
And Monte Carlo.
A Monte Carlo algorithm flips that constraint. It runs in a strictly bounded, highly predictable amount of time. You will get an answer exactly when you need it. But the trade-off is that the answer it gives you has a small, calculable probability of being slightly wrong.
You choose based on what is more important for your system, guaranteed accuracy or a guaranteed deadline.
Exactly. And the course applies this by analyzing a randomized version of the quicksort algorithm.
Right, by picking a completely random pivot element in quicksort, rather than just the first or last item, you virtually eliminate the chance of accidentally hitting its worst-case scenario.
Which reliably brings the sorting time down to O of n log n on average. It's a brilliant workaround to structural intractability.
Which brings us to the final, and perhaps most urgent section for our deep dive today, the final stage of the map, hacking the exam. To actually ace this test, you need to understand how the test itself is engineered.
Looking at the official course assessment and outcomes, the entire course is worth 150 marks. 50 of those are your continuous internal evaluation, attendance assignments and series tests.
But the big beast is the end semester examination, the ESE. It's 3 hours long, and it determines the remaining 100 marks.
The ESE is divided into Part A and Part B. Part A is mandatory. You face 10 questions, 2 from each of the 5 modules, worth 3 marks each.
That's 30 marks of rapid-fire foundational knowledge, defining asymptotic notations, stating Master's theorem, or showing a basic union operation.
Then comes Part B. This is where the heavy lifting happens. You will see 2 full questions from each module, and you must pick one to answer. Each question carries 14 marks, usually split into a 7-mark and 7-mark subdivision.
But how do you actually study for this? This is where the syllabus reveals its secret weapon, the Bloom's category assessment pattern.
Right. The university explicitly uses Bloom's taxonomy to design the test. 30% of the marks are for the remember category, 30% are for the understand category, but a massive 40% of the exam is dedicated to apply.
So what does this all mean? That 40% apply metric is the trap. It means rote memorization will only get you a 30% on this paper.
Yeah, just memorizing a paragraph explaining what Dijkstra's algorithm is will get you almost nowhere in Part B. You have to be able to physically execute it.
When you look at the sample paper for Part B, it's not asking for definitions. It says, find the strongly connected components of this specific graph.
Or it gives you a table of weights and values and says, find the optimal solution for this fractional knapsack problem. It asks you to apply the branch and bound algorithm to solve the traveling salesman problem and draw the state space tree.
Drawing the state space tree, that is pure application. You have to take the control abstractions we talked about and act as the computer compiler yourself on the paper.
Exactly. If you spend all your time reading the textbook and none of your time working through the examples with a pencil, you will be caught entirely off guard by that 40% requirement. You need to practice inserting nodes into an AVL tree and physically drawing the rotations until it becomes muscle memory.
Incredible. Okay, let's look back at the map we've built. We started by mastering Big O notation and the Master's theorem to mathematically measure our code.
Then we organize data by tracing AVL tree rotations and finding strongly connected clusters in graphs.
We open the General's playbook, contrasting the short-sighted greedy strategies with the sticky note table building of dynamic programming and mapping out backtracking.
We hit the wall of NP completeness, using Sudoku to understand verification versus solving, and learning to survive with approximation and randomized algorithms.
And finally, we hacked the Bloom's taxonomy of the exam itself, realizing that physical pen and paper application is the real key to the kingdom.
You really do have the complete architecture of CST 306 in your head now. You know exactly what the examiners value, you know the underlying philosophies of why these algorithms were built, and you know where the heavy lifting is required.
You have everything you need to conquer this paper. Just sit down, draw the graphs, trace the code, and you will ace it.
As you go off to study, I want to leave you with one final thought to ponder. We just spent this entire deep dive looking at rigorous math, precise logic, carefully balanced tree structures, and optimality principles. Everything in algorithm design seems to be about absolute deterministic control, getting the machine to do exactly what you want perfectly.
Right, it's all about order.
But the syllabus ends with randomized algorithms. After an entire semester of trying to build the most logical, rigorous systems imaginable, the computer science community had to admit defeat against the universe's hardest problems.
Which is pretty humbling.
It is, and their ultimate solution, the best workaround for the most complex limits of computation, is sometimes just rolling the dice. Nature's chaos embedded right into our perfect logic. Good luck on your exam.
Good luck.